Today we're going to look at the idea of proof. And the first thing I want you to do is think, what do these three words mean to you mathematically? Conjecture, proof, and theorem. So please pause the video now and think. Okay, I'm going to talk about what they mean mathematically. So a conjecture is when somebody, maybe you, maybe somebody in history, has looked at a bit of maths and they've generalized it. They said, I think this is always true. One example would be here's a triangle, and somebody at some point would have said, right, I've got my triangle here. I believe I've done some measuring, and I believe that the angles in the triangle add up to 180 degrees. That would be a conjecture. Now, the proof would be showing beyond all uncertainty that it's true. So we can't just draw lots of triangles. We need to do a bit more than that. So we can maybe do it mathematically. We can show mathematically that it must always be the case. We've got to assume we've kind of defined what geometry is, we've defined what angles are and what 90 degrees is and so forth. So some things come before that, but then we can, once we've got understanding, we can get on to proving this. So what I'm going to do is I'm going to try and prove it. I've got my angles outlined, and I'm going to call this one A. And I've defined my triangle, so this base is horizontal, and I've done some dashed lines that are all vertical. So if we've understood what 90 degrees is, then we can say that this angle here is 90 minus A. And then I can use the fact that I've got alternate angles here. I've got a Z angle going on. So that's going to mean that this angle here is also 90 minus A. I can then do the same thing with this bottom angle. I can maybe call this B. That's going to mean that this is 90 minus B. And I've got another Z angle. Here it is. And that's going to mean that this one here is also 90 minus B. So if I want to add my angles up in my triangle, then it's going to be A plus 90 minus A plus B plus 90 minus B. And we see actually the A's are going to cancel. I'm adding and subtracting an A, and so on with the B and the minus B, and I'm going to get 180. So without actually doing any measuring, I can show algebraically that my conjecture is true. The proof is complete. As long as I've understood these things beforehand, I can know without any doubt that this must be the case. One thing I've done is I've assumed this alternate angles thing, and I've assumed about 90 degrees and so on. So you can see that maths builds on top of earlier facts, and that's going on to this day. People at this current time that I'm giving this video are doing maths and building on results from last 10 years, maybe the last few months, maybe thousands of years, and they're coming up with new maths. And this is a continual process, and often it's building on simpler concepts. So once you've proven your statement, it's no longer a conjecture, it becomes a theorem. That's what this latter thing is in maths, and that means it is a statement of fact. But to become the statement of fact, we need to prove it. So Pythagoras wasn't actually the first person to discover his fact about right angle triangles. It was known in about 2000 BC by the Babylonians. There's not actually any evidence he was the first to prove it even, but somehow he's got his name after it, and sometimes that happens. So you might want to think if you know any other theorems and if you know of any mathematicians that maybe have things named after them. I've got one other comment to make, in that people are still coming up with conjectures, and sometimes conjectures take a very long time to prove. And here is one more example, the twin prime conjecture. So we know that there are an infinite number of prime numbers, and I'm going to look at that another day, about how to show that's true. It can be proven to be true that there's an infinite amount. There's another statement that says there are an infinite amount of twin prime numbers. So that is, you've got a prime number, and then you've got one that's just two after it that's also prime. So some examples are 3 and 5, 5 and 7, 11 and 13, 17 and 19. Okay, there's lots at the bottom end, but they do thin out. So if you look at the prime numbers between 1 million and 2 million, there's about 70,000 prime numbers between that 1 million numbers. Only 10% of the numbers are then the prime numbers are then twin primes. So it's getting less and less. That also happens with prime numbers as you go on up. They never disappear, but they become sparser and sparser. So the conjecture is that there are an infinite number, and no one has managed yet to prove that. Some people are working on it at the moment as I make this video, but this is a modern day conjecture, a statement that people think is true but has not yet been proven to be true. The type of proof we're going to focus on today is proof by deduction. That is essentially what I've already done with the triangles example. But we're going to go into a little bit more detail and a little bit more complexity. So I'm just going to go straight for it and say we're going to prove that the sum of the squares of any 3 consecutive positive integers cannot be divided by 3. Let's do an example of that to try and get our heads around it. Prove that the sum of the squares of any 3 consecutive positive integers. So I might try the simplest one, 1 squared plus 2 squared plus 3 squared. That is my sum of my squares. That's going to give me 1 plus 4 is 5, 5 plus 9 is 14. And I can see for this particular case, this is true. However, there are an infinite number of positive integers, consecutive positive integers even, so I need another way of doing it, and that's what this proof idea is. So somebody at some point has spotted this and thought, right, it's always true, and then proven it to be true. And this is something you can be trying to do in your maths. It's definitely not, it's a high level sort of skill, but if you can get to the point where you're making predictions and seeing if they're true and just playing with the maths, then you're developing into an excellent mathematician. Okay, so we're going to do it. We're going to show that it's always true. So the sum of the squares of any 3 consecutive positive integers. So I'm going to say my first one is n, and then I'm going to be squaring it. Now, the number that comes after n is going to be n plus 1, and I'm going to be squaring that. Notice I need the bracket around the whole thing. I'm going to be adding them together, and then my third one is going to be n plus 2. Okay, so I'm going to be interested in finding the sum of this. For that, I'm going to need to expand my brackets. So this bit here is going to become n squared plus 2n plus 1. And this bit here is going to become n squared plus 4n plus 4. I don't need the brackets there, actually. I've got no negatives, so I'm just going to rewrite it without the brackets. And then I'm going to collect my like terms. I've got 3 lots of n squared. I've got 2n and 4n. And then I have a 1 and a 4. How do I know that this cannot be divided by 3? To do that, I need a little trick. So what I'm going to do is I'm going to rewrite my 5 as 3 plus 2. And the reason I've done that now is that I've got a common factor of 3 in these first 3 terms. So I can take that out and I can write 3 n squared plus 2n plus 1 plus 2. This thing here will always be a multiple of 3, so that will be divisible by 3, but this 2 won't be. I will always get 2 as a remainder when I divide by 3. So I'd probably just write that down, not divisible by 3. And I'm completed. I've done it. I've shown that it must be the case algebraically. Okay, and that is the idea of proof by deduction. So essentially, we've got a conjecture, and then we're using known facts or theorem, we're showing logical steps, and then we get to the end of the proof, just like I did there. So that is the idea, really. If you're doing consecutive numbers, then just use n and then n plus 1. If you are dealing with odd and even numbers, here's something you need to be aware of. You can always write an even number as 2 times n, where n is some other integer. And you can always write an odd number as 2n plus 1. So you've got an even number and then you're adding 1 to it. These can be really useful when dealing with even and odds, as they've done here. So the statement is, I'm going through this one quite quickly, but just to show another quick example, the product of two odd numbers is odd. So we can take our first odd number as 2p plus 1, you don't have to use n. The second one is 2q plus 1, multiply them together, and then again do a similar trick to what I did before. Take out a 2, have something in the bracket, and then plus 1. That is the definition of an odd number again. It's just that this 2pq plus p plus q is something else. It might be m or something, and then it still fits into this odd category. And that is another example of a proof. So you have to, these are just a bit more advice, you have to state any information, show your steps clearly. Sometimes it's okay to make certain assumptions quickly, like I did with the triangle example. I just said, right, these are alternate angles, but it has to be clear what you're doing as you go along. And then, yeah, then you get to the end of it, okay? Okay, we're going to look at two more proofs just to illustrate the power of proof by deduction. First one is to prove that these 3 points are the vertices, the corners of a right angled triangle. First thing I'm going to do is I'm going to draw my axes and I'm just going to put roughly where I think these points are. So this is A, 1, 1. B is going to be about here, 3, 3. And then C is 4 along and 2 up. It's going to be about here. I can join that up roughly. And I'd say I'm probably talking about this one being a right angle. That's going to, this little sketch has given me a little bit of a feel for which one to focus on. Okay, there are two ways, two nice ways of showing that it's right angled. The first way that we're going to look at is we're going to show that AB and BC are perpendicular. So I'm going to say that the AB, the gradient is going to equal 3 minus 1, okay, the y value subtracted, divided by 3 minus 1, the x value subtracted, and that's going to give me 2 over 2, or just 1. I'm going to do the same for BC. I'm going to call that one M1 and that one M2. For BC, it's going to be 2 minus 3 divided by 4 minus 3, and that's going to give me minus 1 over 1, or just minus 1. I've then got that M1 times M2 is equal to minus 1, and AB and BC are therefore perpendicular. That is the definition of perpendicular lines. If lines are perpendicular, then the gradients multiply to give minus 1. Or if the gradients multiply to give minus 1, the lines are perpendicular. And that means that angle ABC equals 90 degrees. I am done. QED. Okay, second method is we're going to We're going to check Pythagoras' theorem. We're going to find the lengths of the sides. So the length of AB is going to equal the difference between them, 3 and 1, and then I'm going to square it, and I'm going to square root it. That's going to be length AB. That's going to give me the square root of 8. Length BC is going to be the difference in my y's squared plus the difference in my x's squared. 1 squared plus 1 squared square root. That's going to be root 2. And then length AC is going to be 3 squared plus 1 squared square rooted. That's going to be root 10. And I find that if I do AC, I'm going to use the largest one as my hypotenuse. AC squared will equal 10. AB squared plus BC squared will equal 8 plus 2, which equals 10. And therefore, sorry, I'm running out of space, just bear with me. Okay, therefore, I can write down that AC squared equals AB squared plus BC squared, and the triangle is right angled. Pythagoras' theorem is true. Pythag true. Triangle must be right angled. Okay, so you might have done proofs like that before in geometry, but we're sort of putting it all together in one topic now. That's the idea behind proof by deduction. You might just be asked to apply it to lots of different situations, and it's all about step by step, using facts that you know, finding these things out and trying to prove a statement. Last example, prove, so the equation kx squared plus 3kx plus 2 equals 0, where k is a constant, and it has no real roots. Prove that k satisfies the inequality as shown. Okay, we need to use this fact here. If it has no real roots, then that means b squared minus 4ac is less than 0. I'm going to write that straight down. In my case, I've got b here, I've got a here, and I've got c here. So I can write down that b squared minus 4ac equals 3k squared minus 4k times 2, and that is going to be less than 0. So 9k squared minus 8k is going to be less than 0. This is a quadratic inequality. K bracket 9k minus 8 is less than 0. We always solve these by factorizing, and then an important method at this point is to put your roots on a diagram. This is 0, we've got a 0 root, and then we've got 8 over 9. It's a positive quadratic. So if it's less than 0, it's going to be less than 0 here. And so I can write down that 0 less than k less than 8 over 9. Now hold on a minute, that's not what's asked to prove. In the proof it's actually got an equality sign here, but we know that's not the case from here. So what's going on? We just need to investigate when k is equal to 0. So when k equals 0, this is what's going to happen. When k equals 0, we no longer have a quadratic. When k equals 0, we're just going to get that 2 is equal to 0. This also has no solutions. Because this is not true. 2 is not equal to 0. And so we can add this extra little bit on, that actually we can put an equality sign there, and our proof is complete. Done.